Hey guys, welcome to Great Learning. Machine learning is a fascinating process that is considered as a foundational concept for the future. But to understand how machine learning truly works, you have to understand how the data is fed into the algorithm and to get it to train on the data and eventually test it, right? On the whole, it seems like a very simple process, but just feeding the data into the algorithm in any fashion and expecting it to work at good efficiency will not always happen. Now, cross-validation is an extremely important concept that has the capability to elevate a decent algorithm into performing extremely well. Since it is this critical for you to know, we here at Great Learning have come up with this course on K-fold's cross-validation to help you understand it completely. A good amount of theory and hands-on sessions are discussed to help you understand all of this in a very easy to understand manner. With that, I know you guys are super excited to get started. Well, what are you waiting for? My name is Anirudh Rao. Let's go.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell. This is done to make sure you do not miss out on any of the new updates or video releases from Great Learning. And of course, guys, if you enjoy this video, show us some love and do like this video. Knowledge increases by sharing, right? So make sure you share this video with your friends, colleague, and everyone who can make use of it. And at the end of it, make sure to comment on the video if you have any queries or any suggestions, and I'll be more than happy to respond to all of your comments.
So guys, coming to the agenda of this particular course, K-fold cross-validation, let's begin this by understanding what cross-validation is. Now, there might be many instances where we might have actually used this concept in real life ourselves, but we do not know that that might be the name associated with a machine learning concept. So let's begin by understanding that, after which once we know what cross-validation is and know how it works, you'll be very curious to understand where does it fit in the world of machine learning, because as you might have already figured, K-fold validation is very important for machine learning. So we're going to understand by taking a look at how machine learning works as well. So let's take a quick overview of that. Let's have a small understanding on it, and after that is done, we will make sure to take a look at understanding the entire process that governs the world of cross validation as well, right? So it's a multiple step-by-step process through which this works, and we are going to find out how it works as well. After that, we're going to take a look at the various types of cross-validation, because once you've understood how it works, what the process is, the next thing you'll be very curious to find out is, okay, if this is how it works, are there more subdivisions? Are there anything more modular that we can consider to maybe hunt for a niche problem and solve that? We're going to take a look at all of that. And of course, at the end of it, we are going to take a look at a couple of code snippets wherein I'll be demonstrating how easy it is to work with cross-validation, yet at the same time, how much of an impact it can have on the solution itself, right? So all of this are in discussion on this particular course. I know you guys are excited, so what are we waiting for? Let's start with the first item on the agenda, which is introduction to cross-validation. Now, ladies and gentlemen, when the talk is about cross-validation, let us try to connect this concept with our real lives and say, have we used this anywhere? Right? Before we even take a look at what it is, let me tell you a small story. When we say learning, there is a reason the domain is called as machine learning, because you're teaching the machine and it is learning something, correct? So similarly, let us step back a second to look at how the learning happens in our real life as well. Let's just say that you're a college student right now, you're in school, you're in college, or you're a working professional who has gone through an education itself, right? So once you're in that position, you will realize that, there was a way that you had to learn, and there were multiple examinations, Viva sessions, whatever it is, where you had to prove what it is. You had to learn, take a lot of things, put it in your knowledge base, and eventually convey it back correctly later as well, right? That process of you learning, retaining the learning, and eventually giving it out back, that is very important, right? That happens in real life. We learn a lot of different things every day, even though we might not be looking forward to that particular thing. Consciously, we might not know we're learning, but of course, right? The way the intelligence system works in our brains is absolutely fantastic. So coming back to the story, you're a person in college and you have multiple assessments to clear, and eventually, even if you're not a person who might have been in college to relate with this, just take a look at maybe that an examination that you are probably willing to clear in the recent present as well as recent future itself, right? So You know that you're going to be tested. You know that you have to learn. So what do you do next? You gather data from all the different places out there, right? There's multiple online sources where you might be learning from. There's probably a lot of textbooks you're going to have to refer, course manuals, be it online courses, any other material out there as well. So you're going to use all of that and eventually start learning yourself, correct? It seems like a very simple process, but we are taking a very structured approach to understand it. First, you know that there is a problem. The problem is you have to prove your knowledge. Next thing is you're going to need some data to actually sit and understand where all you can learn from, what all should you learn, how should you learn. Correct? Once you're clear with all of these, once you realize, okay, so this is what is required for adding this concept onto my knowledge base, later what do you do? To test yourself, if you have the textbook open right next to you, your eyes is going to eventually go there, and it is not called as a test anymore. But once you close your textbook, once you try to recall from your memory genuinely and you put yourself to the test, that is when you will realize exactly what it is that you learned, which concept maybe which wasn't very clear to you, or something that you might have skipped, all of those things, right? You'll have a clarity, you have an assessment, you have a way to analyze, saying, hey, after this test, I can go back and say, this is what I should have done, right? There is a correction method also there. So there are so many things that's going to come out of a very simple process of learning and eventually assessing what it is that you have learned. Now, I'm sure you can try to guess where the story is going with respect to how machine learning might work as well. Step number 1, you decided you want to learn something new and you eventually went ahead and learned it using online resources or whatever it is. After that, you said, hey, now I want to see how much I have learned. So eventually you had to assess yourself and you had to see if your learning was up to a requirement. When I say a requirement, you might be having a problem statement that you have to solve. So you check that out. If it is correct, if it met the requirement, you would say, okay, I have learned this. If it hasn't met that requirement, you would say, okay, let me go back, let me revisit and eventually try to assess and analyze what went wrong, correct it, and eventually come back stronger, maybe to get more marks or whatever it is, right? I'm just giving you one college example. This happens almost in all the walks of our lives, right? Similarly, when you're training a machine learning model as well, these are some of the things which you have to keep in your mind. Now, with this understanding, you might have a question saying, okay, so what is cross-validation? How is it related to this process of studying, and why do we even require it? Let me answer that question. Now, when you say what cross-validation is nothing but a methodology that we actually use to have a better way of assessing, to have a better way of understanding how we can track the performance of a machine learning model. In real life, your performance is tracked by your report cards, by the marks you might have obtained on your courses. Correct? Similarly here as well, even though we're not directly looking at report cards, we're trying to understand what is a methodology that we can use during the process of learning itself that can help us, right? Now, of course, you would have done this whenever you're learning using books, online resources as well. You would have thought that, hey, this is how I'm going to learn the concept. But when you see someone else teaching it in a different way, you'll be like, oh, okay, so I can change my own way of learning, or I can change the style through which I learn, or maybe the pattern, learn once, exam again, or learn everything at once and just one final exam, right? So you will find new ways to understand how things might work. Now, what is the important thing you have to know about cross-validation is that it is extremely important for machine learning. Even though when people say, okay, we can get away without doing cross-validation, I'll say, yes, you can get away. Your model can definitely be 90-95% accurate also. But for the few of us who are looking for that to make a mark, for the few of us who are saying, hey, I want my algorithm not just to be good, not just to be better, but it has to be the best at what it is doing, and you're going to do everything you can to do that point, right? So when you are hunting performance, when you're hunting for tractable metrics, especially in the world of machine learning, every single point, right from you understanding the problem statement all the way to you finding data, how you find data, here is the important part. How you provide the data to your machine learning algorithm for it to learn is important, right? Now, you might ask saying, okay, where have I done this in real life? If you know, your textbook is very nicely put together, right? Everything is divided chapter wise, heading wise. There's an index page. You can see a lot of modularity and what structure to the content. That is also what is required for us. Let me tell you this about cross validation. It is considered so important that at the end of the day, you can say that, hey, without cross-validation, I have maybe 50% accuracy in my model, but with cross-validation, I might have 75, 80%, and with further tweaking, you can get ahead as well. So taking your model from being, okay, this might not work for us, all the way to, yes, this model works fantastically well at its best efficiency ever. That is the gap basically that we're trying to bridge here. We understand why it is required, but where does it fit in the world of machine learning? To understand that, we have to take a look at and revisit one or two concepts in machine learning to figure out, okay, if this is the case, where will it work, right? So let's quickly take an overview of understanding how machine learning works. Whenever you're working on machine learning, we start with the business problem. There is a reason why machine learning would be used. You would know that, saying, hey, if this can be done manually and if you can find a way to teach your machine to do it, let's do that, right? So you know what the problem is. You will probably know how to attack the problem as well and solve it in the best way that is possible in your hand. Once you go on to do all of that, the next thing you'll be like, okay, I know that my machine learning model is completely dependent on the data that you provide. If you provide data which is unclean, which is very raw, which is not filtered, which is not correct, at the end of the day, your machine learning model will be learning everything incorrectly and giving you a result which is absolutely providing no fruit to us, right? But in the data acquisition, data cleaning, these two phases itself, if you're very careful about the quality and the quantity of your data, and just like a textbook, if it's clear and concise, the way you will learn is definitely better, right? Your learnability factor will go up. So after gathering all the data from multiple places, you will do some sort of processing to it. You will clean it. If you do not clean it, again, it's a very raw entity. There's a very good chance your machine learning algorithm will catch the wrong pattern, catch the wrong track, and eventually take off there, right? Because even though it is trying to assess itself at every point in its time, it becomes very difficult for your machine learning algorithm to figure it out on its own. That's why we have metrics such as error tracking rates. We have metrics such as accuracy rates, which will tell us, hey, this is what your machine learning model is doing. And if you, once you start understanding the patterns that it starts exhibiting, you will know where it went wrong. Maybe your data is underfitting. Maybe your data is overfitting as well, which is causing to that. There are a lot of outliers. There can be n number of reasons, but most of those reasons, let me tell you, are solved. We will not occur at those errors because of the fact that we'll actually be very careful in the data acquisition and the cleaning stage. Once you go on to do that, you can perform some quick preliminary analysis by making use of a concept called as EDA. EDA stands for Exploratory Data Analysis. It is a concept which is considered to be key because you don't have to have your algorithm work right away to tell you that, hey, this might be what solution you're looking for. You can actually run through the data yourself manually to figure out. You can dig deeper to say, okay, so let's consider a simple example like diabetes. There are many factors that can cause diabetes. You don't have to have your machine learning algorithm model tell you that, right? As soon as you look at certain data sets from certain patients, you can see that maybe not maintaining your blood sugar level, or maybe not looking after your diet, or maybe not looking after your fitness level, or whatever it is, might lead to that. Maybe it's hereditary, maybe it's age. You see, whenever I'm saying maybe, you know that it might or might not have an impact. So with respect to data analysis and the concept of correlation and all of that, you can find out to what degree that particular parameter has an effect on the output as well, right? That is super, super important. This is where all the concepts of math and statistics come into the picture. Once you've performed some basic analysis, the next thing is you're going to be providing all this data in a very important manner to your machine learning algorithm, in a manner that it understands, like a textbook. Now, I'm not saying you're going to be providing a textbook to it, but all I'm trying to say is in the form of a textbook. Whenever I say a textbook, understand that it can be content which is in a structured format. Now, once you go on to provide the data to your machine learning algorithm, next thing is it's almost like it's learning and it has learnt. After that, you tend to predict what it has learned, right? Only then, once you give it an examination, once you give it a test, that's when you're going to be understanding, saying, hey, this is how my model learnt. This is where it can do well. This is where it cannot do things well. After that, this is a process where you're going to be doing it multiple times. Maybe you realize that your data is not clean enough. You're going to go clean it up. Maybe you realize that your algorithm can be different. The way it learns can be different. All of that, right? So you're going to take a look at all of that, retweak it, retune it, and do this process a couple of times. And only then you'll come at a stage saying, yes, regardless of the input that I provide, my model is working well and it is time to deploy it. When I say deploy, it is actually being put to place to solve the business problem. Correct? Now, where is cross-validation coming into the picture? Cross-validation is very important in the part of actually us providing the data to the machine learning algorithm, right? More on this a little later. One important way of whenever you're saying, hey, cross-validation has an impact of how the data is given to the machine learning algorithm, but is there any difference of how you would do traditional programming, how you would pass data to your traditional programming versus how you would do it for machine learning? Yes, of course. When you take a look at how traditional programming works, you're going to be providing a program that serves as a logic, you're going to be providing the data, and eventually the data and the program is going to come together to give you a workable output. Correct? This is how we solve 99% of our problems. But if you're taking a look at machine learning on your right, you're going to be providing it some data. And in many cases of, let's say, supervised learning or anything as such, you'll be providing the output as well. You will say, hey, this is the output that you should get. Here is the data that will help you get to it. Find the structure, find the pattern, find the route between A to B and do it. That is the most important difference between traditional programming and machine learning if you look at it, right? Understanding that even though it seems like the data points might be the same, but knowing that you're also providing the output alongside the data, you're telling it this is what is required eventually and giving the data, right? So you have to be very careful, especially in this regard, when you're providing that data, when you're understanding what output needs to be expected from the algorithm. Right, that is important. So if you're being so I'm going to repeat that. So if you're emphasizing, again repeat. So if you're emphasizing so many times saying that, hey, data is extremely important, without data it's not possible, well, what are we doing with respect to the data? To train a machine learning algorithm, again, the same examination example. You have textbooks, you have examination. So here what we do is we have certain data. Let's just say we have 1,000 rows of data. What I'm going to do is, I'm going to probably give it only 800 rows worth of data to learn. And it knows that 800 rows of data completely. So if you test it on the same thing, it will of course work. It will give you 100% accuracy. There's a good chance. So it's not learning. It's like having your textbook next to your examination paper, right? But the remaining 200 rows, which it has never seen before, if I show that and say, hey, can you predict on this? Can you work on this? That's literally like an examination. And there we can assess its true learning, right? So to do that, we split the data out by the way of providing it to the machine learning algorithm itself. We split it out to be training data. We split it out to be testing data. In the case of training data, what happens is this is the data that is responsible to teach the algorithm. This is the data which the algorithm uses to actually do the learning process. So if I say, hey, this is how it should actually learn. And if I say that, hey, you know what, here's some data for you to learn. And maybe here's a picture of a cat, here's a picture of a dog. So learn using these pictures. Later, when I show you other pictures of cats and dogs, you're supposed to figure it out. Then it can only do that if it has actually understood what the features of a dog are, what a dog looks like, features of a cat, what a cat looks like, right? Unless it has done that, it becomes impossible for it to do, right? So the way you present the data to your machine learning algorithm, the way you actually convey things for it to learn is so important that this process, if done incorrectly, 90% of the chance I can confidently say that it will break your machine learning model. There are so many cases, if you're on these multiple websites where you can, where people come together in communities, ask a lot of doubts, questions and all of that, you'll be very curious to find out people will concentrate so much on the actual learning process itself that they tend to miss this particular aspect. So cross-validation is so important here. If you think that cross-validation, as I already told you, if you think that, hey, it is just another concept which I can do without, maybe yes, depending on your application, you can. Majorly though, if you are not very careful in that league, you'll be breaking your head about why your algorithm is performing so badly when you have not concentrated on things like this. So for efficiency, for extracting that final 1%, the best of the best, I believe it is very important for you guys to understand this. With this, you will be very curious to say, okay, yes, cross-validation is super important. We know where it fits in the world of machine learning and all of that. But how is cross-validation used, right? In this section, let's find that out. So how does cross-validation work? This is a question I am sure you might be asking yourself, right? Well, to talk to you about how cross-validation itself works, let's take a look at some steps. Let's take it in a structured approach to answer this particular question. First of all, whenever I say that it all has to do with the data that we provide to the algorithm, how we are providing the data, it becomes important for you to know, are we changing anything with the data before providing? The answer to that is no, we're not changing the actual data. We probably, in this case of cross-validation, we're splitting the data out into multiple partitions or multiple folds, hence the name k-folds. K stands for any number, right? It can be 1, 2, 3, 4, 5, 10. It can be a positive integer. Now, when that is the case, when you're saying we have to take a large data, break it down into simple partitions, break it down into simple chunks or folds, and then eventually, instead of just saying, hey, algorithm, here's all the data, learn, what we're going to do is we're going to actually take a step back, run the analysis. We're going to do the learning on these tiny bits of partitions of data that we have gone on to cut the data into. Once you do this, you will remove any sort of biases that might exist, which will cause an inconsistent output. At the same time, you'll have really high accuracy rates, because if you take a look at one small data set, there's a very good chance it cannot represent the entire world's solution out there, right? It's of course, it consists of many situations, many analysis factors, points, metrics, features, all of that. But at the end of the day, if you just cram it all into a model and expect it to learn, it will not work. This is where we split it out into partitions. We train and teach each of those partitions and eventually see what works well, combining it out and seeing that, hey, if I cut the data down into 3 parts and run a sprint on it with respect to testing and training, the overall error might actually come down. And eventually, once you do all of these process, look at step number 3. It says average the overall error estimate. Instead of sending it once, getting the learning once, testing it once and be done with it, this iterative process will give you better clarity about which part of the data is your model probably not functioning really well in, where does it work well, how do you, bridge this gap that exists. It's not just the way we provide the data that you're seeing that affects efficiency. Every single tiny thing which comes subconsciously to us will not work for our machine. So we really have to dive into the modular level to understand how things work, right? So the first thing is, for any machine learning model to work, or even cross-validation to work properly, it is vital for you to understand that, hey, this is the correct algorithm to use. Now, you might be an expert in cross-validation, but at the end of the day, if you use a wrong algorithm, it will still probably not work great, right? So it is very, very important that you select, first of all, the correct algorithm that will work for your case. But when you say that, this algorithm works really well, that model does not work well, you have a metric that you're comparing, right? So how are you doing this comparison which says, hey, this algorithm works, that doesn't? What are we doing there, right? So the first step is you train your machine learning model on an available data set. Testing it again on the same data set is absolutely meaningless, like the examination example I gave you, right? The goal is not just for us to say, hey, this is the data, it will work fantastic on this data and it's done. No. The goal here is to say, hey, here is a small snippet, here's a sample space from a population. If you can work on all of these cases correctly, there's a very good chance, very high probability that it will work on all these scenarios that might come up in the real world as well, right? The goal is that to eventually get from this point to that. But if you're just in the loop stuck there, training on that same data, testing on that same data, it will never learn effectively. This is where we're using this concept slightly as a cheat code, where we eventually split that data down into multiple blocks, train it, test it multiple times, and eventually that will help us out to understand this kind of a modular approach that I just explained, right? So all the possible situations which might occur for learning will probably occur when you're doing that. And of course, we have a lot of data to prove that cross-validation is extremely effective and extremely efficient, but that is the case, right? You realize that going to this kind of a depth to analyze just how you provide the data and how you train your machine learning model, it has such a huge impact. Now, it is 3 simple steps, ladies and gentlemen, as you took a look at it. But with this at the same time, you might say, okay, now I know the process of cross-validation. What are some of the various types of cross-validation that are out there? Very good question, because there is many types of cross-validation that you can come across, right? When you take a look at it, k-fold is always the most popular one, which is probably used whenever someone talks about cross-validation. Even when you Google cross-validation, k-folds is usually the first one that will turn up. Well, It is common to assume that it might be the only technique, but no, there's many techniques, definitely more techniques than we are discussing, because the more in depth you go in each of these techniques, you will find one more way to make the product more efficient or make the process more efficient. In this particular case, you can see on your screen that there's many techniques, the holdout cross validation, K-folds, and once you start diving in depth in the K-fold system itself, you'll realize that there can be another method through which you can improve K-folds itself, and that is stratified K-fold, right? So, like this, once you start diving into understanding the variety ways through which you can handle data, push it to your algorithm, get it to learn, get it to train, you will realize that there's two ways to go about it. So the two ways of learning is basically exhaustive methods of learning and non-exhaustive methods of actually doing cross-validation. In this particular case, what we are discussing is K-fold cross-validation, and we're going to be taking a small look at what stratified K-fold is as well, right? Now, in this course, if you just learn K-fold, you will definitely get the knowledge of it. But if we teach you stratified K-fold as well, it will help you digress and understand the concept better. Now, I told you about exhaustive methods. I told you about non-exhaustive methods, right? When you're taking a look at understanding what exhaustive even means, when I say, hey, I want to search something and I want to do it exhaustively, what does it mean? It means that I want to do it to a very good amount of depth, very detailed. I want to be very careful with it. I'm going to spend a good amount of time, and I'm going to not miss anything. Right? Even if it's a needle in a haystack, I'm going to sit and find it. That is exhaustive. Doing it completely, thoroughly, all of that. So if that is exhaustive, what is non-exhaustive? Non-exhaustive doesn't have to mean that you have to give your 110% to eventually put the hard work in to get it done. There is a smart way to go about doing it as well, right? So in our particular case, whenever we discuss about K-folds, or whenever we take a look at even stratified K-fold, that's the reason I've just mentioned fold cross validation. It is a fact that it is not exhaustive. We're not just trying to look at 110% of the data, because if you do that, at the end of the day, there can be issues with respect to underfitting and overfitting too. What we are doing is we're considering a non-exhaustive yet super intelligent approach that is eventually going to get us to our solution. So there's something called as holdout method also, which works on the same lines, but it is a very simple process, and we're going to understand that. But what you need to know is, if I just step back one slide here, right? So all these other methods that you might be seeing, leave one out, leave P out, right? All these types of cross validation, these form to be the exhaustive methodologies. In the exhaustive methodologies, there is no other round. When I say leave none out or leave one out, it means literally apart from maybe one sample or one of those types of ways which you provide data, you literally have to scour through it multiple times and get it to learn, right? Exhaustive. Let's find a smart way to go about doing this. And a holdout method is again a super popular, at the end of the day, again, one of the most sought after solutions whenever you have to think a look at finding a non-exhaustive method that will do your job. So what is a holdout method? You've used this in real life as well. When all this time that I've been explaining to you guys, we have been using holdout method ourselves, because if you have one entire data set as you see here, with holdout method, the most basic approach is to cut it down into training data, to cut it down into testing data. Once you cut it into training and testing, it's a very straightforward process of providing the training data to your model, use it for the model to train and understand. Later, give it another part of the data which it has never seen before, and eventually evaluate the performance on that, right? So the holdout method is common among all the people who are getting started with machine learning, I'm sure, because it works. I'm not saying that the holdout method is very inefficient compared to cross-validation. There are some cases where cross-validation will give you a lower accuracy rate compared to the holdout method. So there's again a lot of analysis, there's a lot of understanding you need to have, saying where I can use what, where things work, where things might not work. Figuring out this in a non-exhaustive method like holdout method, or eventually with respect to K-folds, is very easy, because there's so many ways you can tweak and tune it right there to help you understand this particular metric. But with respect to exhaustive, in my opinion, it can slightly get tedious to get to know all of that. Right? So with respect to holdout method, we know this now. We're going to split the data into testing and training, a very simple approach. But what we do, a common practice is to find out that if you have a large amount of data at hand, emphasis on the word large, if you have a large I'm going to repeat that. So if you have a large amount of data, in your hand, what you will prefer to do is you're going to provide more than 2 times of the data of your testing size to be your training size, right? If you again take a look at it in real world, your textbook is probably going to have a lot more information ever than you have been asked in your examination, right? Maybe you're learning one unit which has so many different concepts, yet in your examination you might get only 2 questions from that. Correct. So the size of your training will always need to be more than the size of your testing. Now, I'm not going to say this is going to work for all the cases, because majority, 99% of the case, this is how it is. Your training data, it can have a better understanding of it and eventually perform well as well, right? On paper, it is good to think that, hey, we can do this way. We have a methodology. It works. It is efficient and all of that. But when you start diving into understanding, do we have so much data that we can give more than twice of it to the training part of it? That becomes a hassle in the real world. So then what we do is we try to find the next best way of how we can do the holdout method. This is where you'll actually split your data into testing and training data sets, and you'll have a ratio of split. Usually in most of these cases, again, I'm sure if you're at this point of time, you might have explored a bit of machine learning yourself, is for a fact that we're going to be splitting the data commonly either 70% for training or 80% of training, right? And when we do it 70% for training, of course, the remaining 30 is going to go to test. Similarly, if you're doing 80% for training, remaining 20 goes for test, correct? So this kind of a ratio has worked really well. There's no magic number to say that, hey, use 85%, it'll always work. Not really. Sometimes it might so happen that you can use 50% to train, 50% to test, and you can have multiple ways, multiple iterations of training it through different ways, and it can get better accuracy rates as well. So how do you figure out, how do you pinpoint and say, this is what I would want to use? This particular part of my data is helping me work. This part of my data is helping my model have its efficiency high. How can you say that? You can only say that if you have the capability to split your data further into smaller partitions or folds or chunks, which at the end of the day will help you get to that point, right? Now that is our K-fold discussion. But just before that, we need to take a look at what happens in a holdout method. It's not directly take the data, cut it out and send it. We also have to shuffle it randomly to make sure that we do not have any sort of biases there as well. Your model is eventually going to use that data. It's going to use a different, it's going to have multiple combinations of data points that it's going to look at and eventually give you a result. But the thing with the holdout method is that it can be slightly unstable, because the training data that you've just given, the 70% of data that you've given, might not represent the entire world out there. Even with your case, let's just say you had 1,000 data points to begin with. You trained it on 700, you tested it on 300, works very well. But now when you provide it a larger, maybe another real world data or very complex data that you think it will work really well with this approach, there it might fail, right? This is where the instability comes in whenever you're trying to use the holdout method. So you can never say for a fact that, hey, this is why my training data set works. This is why a small amount of data I have represents everything out there. No, that is wrong, right? You can never put a point on that unless of course you guys are taking a look at K-fold cross validation, because here there is still certain gray area, but at the end of the day, the way we approach the problem is so radically different that as you understand the process, you will be surprised to find out about why we don't use this every single time, right? So it's first of all, for you to understand the K-fold technique is very much different, and it's a huge improvement compared to the holdout technique that we just took a look at. Now, what we're trying to assess and gauge with respect to K-fold cross validation is saying that, hey, this particular methodology will guarantee that your score of your model will not just depend on how you know what training data you picked or what testing data you picked. At the end of the day, we are trying to give it some sort of intelligence to a point where any similar data with similar features and points that it sees, it should perform on the same level of accuracy. Because if it does not, and if it only works very well on your data, there is no point. If that is the only data it will ever see, wonderful. But 90% of the cases when you take a look at it, so usually you'll be working on a prototype, usually you'll be working on a product. So there is one thing which is very important, is that through this methodology, we're going to say that, hey, our model will not just work for this particular data, it will work for all the other data, and the learning just becomes independent of the data that it sees itself. That is very important, not just for machine learning, but that is also super important for the concepts of deep learning, artificial intelligence, and all all of that. So once you take a look at it, you will be curious to say, okay, now I like where this is going, but how do we do it? Take a look at your screen right now. Right? So what we usually do is, this is a process where you don't send your data once, train it once, test it once and done. That beats the entire purpose. What we do is we split the data out into multiple training and testing chunks, wherein it's an iterative process. In the first iteration, we're going to be only using the first block of it to test and train, and eventually we're going to be retraining it on multiple data points and testing it out on one testing data point, right? Look at this. So we're going to be training in this part of the loop. We're going to be training here, we're going to be training here and here. And once we take a look at this particular point where we test it, we know for this particular type of data or whatever the points it might hold, there we will know if it works well or not. Next, what we do is, instead of retraining those same concepts and retesting on those same concepts, we are going to move one step, right? So we're going to be training another set of data which it has not seen, and now we're going to be testing it on a data which probably it has not seen in this particular iteration, right? You might say, hey, if you've already trained it here, why in the next iteration will it still retain the training? The process here is very important for you to understand, is that each of these is a training step and each of those is a testing step. So whenever it retrains, it will have to figure out something. We will need a metric to track, which is the error rate and accuracy rate. What it needs is basically more exposure to the data and more understanding of it. This is where we run it like a little cheat code of ours, where we split the data, we get it to train multiple times, and we get it to train on multiple, we get it to test it on multiple different data sets, through which, when I say different data sets, the different chunk, the different fold in that particular data set, through which it will understand that, right? You're basically tricking your model to making it understand more data, even though when you have only a small amount of data, through which it's a very simple concept. It's like you running on the street, right? If you're a person who's a marathon runner or something, you can run 30 kilometers in one direction and you can probably walk or run 30 kilometers back. But if you're just looping around your house for 30 kilometers, maybe it's convenient to get back home quicker, right? Because you've been running around there itself. So if you change your mind, if you feel that there's a lack of efficiency anywhere, you can quickly call it quits. Now, here, that kind of an analogy will also work, because once your model reaches the level of accuracy or reaches the level of expectation and that's met, it has done training. You don't have to waste further time. But when you take a look at how we actually do it on the micro scale, this is how it is, ladies and gentlemen. You have to understand each and every step that goes into this. The first step for us is to actually split the data randomly into k folds. That's how the name has got. K is a number, right? When I say we are splitting the data into 2 folds, we're basically cutting it into 2 subsets. When I say the k value is 3, we're doing a 4-fold cross validation, 5-fold, 6 folds. It means that we're taking the entire data, randomly splitting it out and breaking into these many chunks. Now, for every single chunk that you actually create, that particular chunk will remain to build your model, and everything else remaining. If you have picked up 5 chunks, if you have created 5 chunks and you picked up 1, how many are remaining? The 4 chunks that are remaining, right? So for every single chunk that you actually cut out, you will train the model in that particular case and eventually use all the remaining training with respect to that one you cut for testing purposes, right? Look at this. We're just going to make 1, 2, 3, 4, 5. This is a 5-fold cross validation. In this particular case, we're going to be doing 4 instances of testing for each iteration. And even though it's k, even though k is 5 here, we're going to be testing it on the k minus 1. In this particular case, it is important for you to understand that with every observation that we pick up from the original data set, that it has a presence in both the training and the testing data set, right? It's like you having a textbook, in your head, even though it's physically not there with you. With every observation you would have made while learning through the textbook, it's there. You have run through it. You have run through the entire textbook once. Instead of just doing it once, in this particular case, it's done multiple different times to make sure that there is a chance that data point would have appeared for training, that same data point would have appeared for testing it as well. Again, this is how we use it in the real world itself, but once you're diving into the modularity, you will understand that doing it this way will ensure that any bias that you might have with respect to how your model works, that bias will go a lot low. It will go down. That way, when your bias goes down, when your error is going down and your accuracy rate is going up, your model is going to work fabulously, right? That is the goal that you have to understand here. Now, usually one question that I get asked is saying, okay, so if we have hold out method which works really well, if we have k-folds which also works really well, where do we use both? How do we use it? In the case, in the situation where you have a large amount of data, right, a huge amount of data that you can use for training and testing, you can directly use the hold out method. But if you have limited access to data and you still want to run through every single permutation and combination that it can use to learn and test, you would be considering k-fold cross validation, right? But you might be asking another question saying, okay, so all this time we have only been discussing the advantages of it, saying it's amazing, understanding why it is amazing, but can there be a situation where there are disadvantages also? Of course, there are disadvantages. The first disadvantage that you will have to think about is the number of times we are training the model, right? Let me quickly go back here. Instead of just, let me go back, in fact, to the holdout method here, right? Look at this image. You're cutting the data set out into training and testing. You're training it once with the training data, testing it once with the testing data. You are done with it, right? But in our case of what we are discussing with respect to k-folds, we are cutting it out into multiple pieces, running over them multiple times as well. So what's happening? Instead of training it once, now we are training, so many different times as well. Each iteration has multiple trainings that it has to do. And with every single training point, it can later become a testing point. And of course, it will become a testing point later as well. The number of times it has to learn will go exponentially up. And one disadvantage is that, again, if you have slightly larger data set, it will result in an overall slower process of learning. Slow doesn't mean it's bad. In my opinion, in this case, it's good, because even though you're running it k number of times, k can be 1, 2, 3, 4, 5 or anything. So if you're running it so many times, the advantage is that it will learn so much better. The disadvantage is that it will take that time. It will have to retrain. You'll have to go on training it that many times, right? So instead of it taking, if it takes X amount of time to train, if you're just using the holdout method, here it will take k into X time. So if you're doing a 5-fold cross validation, it will take 5 more times of effort and time to actually for it to learn, for it to train, for it to verify and give you a usable output, right? It's only time which is of the essence. And even though we can simply say, hey, it's okay, I have a lot of time, let's just use this. Correct. When you're working on a very complex industrial level data set where you have to quickly go from prototype to product, or if you have to quickly assess what's wrong or how can you make the process better, this is usually a process you would slightly you would go out with the holdout, try it out, and eventually then start doing this. That's the reason whenever you're learning machine learning as well, you go to the simplest process, understand how things work, and once you start tuning it and stretching towards that final 1%, that extra bit of performance you're looking for, then you will be taking a look at k-folds, right? So once we understand what k-fold is, we understood how it works, we know the process now. What is this something called as stratified k-fold cross validation, right? Why do we even need stratification when we're talking about k-folds? See, one thing about k-fold is that we're going to be, first of all, shuffling the data in a random manner while breaking it up, right? We're going to be breaking up into multiple folds, multiple patterns. But one thing you have to consider is that even though you are trying to break it into multiple chunks, one chunk can be very, very biased compared to the other one. So when you're training it on that, your accuracy might be super high. But once you start training it on a different data set and use that as your testing data point, your bias will come into the picture so much that it'll say, hey, accuracy is 95%. As soon as you move to some other point, it can say accuracy is 60%. Now, this huge, performance difference is usually seen because of the fact that even though you're randomly cutting something out, it never is truly random, right? Think about it. There can be a pattern to almost everything in today's world. How do you think your computer does anything in a random fashion? When I say, hey, I'll give you 1 to 10 numbers, give me a randomized output, of course it will still work. But you realize that it is using a calculatable, metric-driven algorithm or a function or a process to do that. So at the end of the day, if you figure out how that process itself is working, it is no longer random. Do you agree with me? That will blow out of proportion with the case of using k-fold. So that's the reason why we use stratified k-fold as well. So to give you an example, to give you understanding of how we're trying to sort of solve that problem with respect to stratified k-fold, let's just say that if we have a case where we have a fold which has majority of all the positive classes. Maybe we're just trying to assess if a person is diabetic positive or diabetic negative. So in one fold, even though we randomized it, there can be a case where there are a lot of patients who are diabetic, and maybe only very few who are not diabetic as well. So once you start training on these parameters, no matter what data it might see later of a non-diabetic person as well, it learned it incorrectly. It will say, hey, now, I learned it where there's a lot of positive bias, and of course, this person also has diabetes, right? So it is incorrectly predicting that someone actually has diabetes when they don't. That is a very big mess. And in fact, if you're taking a look at understanding the metrics of accuracy, true positive, true negative, false negative, those numbers will go up and up, right? Especially the negative cases, all the wrong cases, those will go up really, and your accuracy will just tank down. That is the problem we have to solve. So how are we doing it with respect to stratified k-fold? What does stratification even mean? To answer your question, stratification is nothing but a very simple process of how we go on to rearrange the data into that particular fold, so that once we do it, we are trying to bring the bias down. We're trying to find a structured way of removing randomness in the data, and at the same time making sure that your data has a good number of positive cases, a good number of negative cases as well. So when it learns, right, especially like a situation where we have to do a binary classifier. A binary classifier just has two classes, an image of a dog, an image of a cat. Now in this particular case, if we just have to use this, we can, for every fold, don't you think that we can have 50% of dog images, 50% of cat images, and then use that fold to train, so that it is learning equally in the terms of dogs, it is learning equally in the terms of cats. This kind of an arrangement where we are removing the random bias completely to say, hey, this is how we can even solve one more problem through an already efficient process, is exactly what we're doing here, right? So each class here will again comprise of half the instances through which it has to figure out. Your learning is good, it will learn really well, very good chance that your model accuracy is gonna go up and work really well as well, right? So you understood the difference between k-fold and stratified k-fold, I'm sure. K-fold, cut the data out randomly, cut it out into multiple folds, train it multiple times. But your data can never truly be random, because there is a mathematical tractable function which is working to create some sort of a sense of randomness. If you're very intelligent and you dive extremely into the depth, you can work your way back and say this is not random, here is why. But instead of just relying on the randomness and saying it may or may not work, what we did with stratified is we eventually broke it down into classes. We made sure that there were equal number of instances while it trains, so that it can use it better for training, right? All right, guys, with this, we have understood, what cross-validation is, why we require cross-validation, how does it work, where does it fit in the process of machine learning, how can we use it, what are the various types of it, are there any downfalls, if there are any downfalls, how do we fix it? We understood all of this in theory now. It's time to take a small look at a practical example to understand. Right now, you have to know that with respect to k-fold or stratified k-fold, it is very much dependent on the quality of the data that you provide and how your data is not very skewed. Now, if the data, the entire data that you're providing is just 90% of positive cases, 10% of negative cases, and you're asking it to figure out negative cases, it's going to be very difficult. So it's also vital to consider data cleaning, data pre-processing before even figuring out how you would provide your data to the learning and how you get it to learn. That is something you need to keep in your mind. So right, guys, now with this, what we can actually do is we can dive right into Google Colab. Google Colab is a Jupyter notebook that is hosted on the Google Cloud platform. It works very well for any sort of Python or R programming code, and I usually prefer this kind of an environment to work in. If you guys love working with Jupyter notebook, it's very, very, very similar as you'll see it. For the people who are using IDEs such as PyCharm, or you're using an instance of Anaconda or something like that, of course, since it's Python code, it will still work there, right? Alright guys, so I've come to the Jupyter Notebook and basically Google Colab, and as you can see we're going to be discussing a lot of things quickly. First of all, we're going to assess and understand the small k-folds example to see it's working. Next, we're going to remove the randomness and we're going to be working on stratified k-fold. You're going to see implementing it in code is actually super simple. And after that, let's quickly take a look at making use of logistic regression on a data set to understand how k-fold will improve its performance as well. Right? Super. Let me zoom in so that you guys can see this better. Now, I told you that with respect to k-folds, k is basically a number, right? That is the number of folds that we're going to be using. In this particular example, what we're basically trying to do is we're breaking it down into two folds. We are cutting the data set into two folds where each of these folds comes with 4 samples, 2 for training, 2 for testing, right? It's very simple, ladies and gentlemen. So whenever you have to work with k-folds, it is directly available in the scikit-learn library. Now, why do we use scikit-learn library? It serves as a foundational concept to achieve machine learning, to use machine learning with respect to Python. Why do we use NumPy? Because we're trying to create a data structure, as you'll see in the next couple of steps as well. When we go on to use the NumPy indexing, we can split the data out into testing and training very easily. Now, what are we doing? How many? We have 4 data points, of course, and we're splitting it into 2 folds with 4 elements in them. Now, as soon as I run this very simple piece of code, all we're trying to do is take those 4 points of data that we have, cut it out into 2 folds, and find a way so that you can have oneness testing, train on the remaining one, and eventually swap it and do the same process in a multi-iterative stage, right? So as soon as you saw the output, it is showing that we have even though we are seeing the same data here, you're seeing multiple ways of how we're getting to that data. You're seeing the folds through which your data has been broken in fact, not broken in, how it's been split into, right? So it's very important for you to understand this with a very simple example. Now you can have more data points. You can have an actual data set through which you're going to be splitting it out into maybe not 2 parts. If you're working on a very large data set, you might say, hey, I'm going to require 10 folds. I'm going to require 4 folds. There is a way to analyze how many folds as well. So if you say that, hey, my algorithm will work very well between 2 folds and 10 folds, you're going to train it for those 2 folds. You're going to cut the data into 3, 4, 5, 6, 7, 8, 9, 10. Your time that it takes will exponentially go up. But at the end of it, you will figure out what fold will give you your best efficient result. So when people are very critical about performance, especially like all the applications that we use, I am very sure that this will be done this will be scrutinized to a very good degree there. Right? So if you are taking NumPy indexing, if you're actually providing certain data to say, hey, here is an array, here is all the data that is required, you can see with respect to one line of code, we can actually split the data out into training. We can split the data out into testing, right? Each fold will of course have, whenever you're breaking something into folds, understand that each fold will have training, each fold will also have testing. So as soon as I run this piece of code, this NumPy array that we see as an input using NumPy index, all we have done is we have split it very conveniently, keeping it ready for training. The same data is also ready for testing, of course, in the next iteration, right? So understanding how we use k-fold is very simple. The part where which you'll gain by experience is figuring out how many folds to use, where to use, through which algorithm can your model start working effectively well when it talks really well to k-fold, right? So that was k-fold. Now, what is stratified k-fold? There is not a lot of difference here, ladies and gentlemen. Again, you're going to be importing it from the same package, sklearn, and here we have a couple of input elements that we are providing to it. But the important thing you have to assess with respect to stratified k-fold is look at the training data, look at the testing data, right? With respect to your training data and testing data, now all we have given is we have created a couple of data points. You'll see that each of them, whenever it gets broken down, right, the elements, the entities, we've removed the randomness, we've removed the random bias which might occur here, and we're saying, hey, we're going to be binning the data separately for training and testing. And once we go on to print what the data that bin holds with respect to the NumPy bin, you will figure out that, hey, all this data points consists of equal number of elements when we use it for training or when we use it for testing. Let's go back to that dogcat classifier example, right? You have broken down a data set into 2 folds. You know that there'll be 2 iterations with respect to one particular iteration where one is training, the other one is testing. Later that becomes training and this one is testing. Each of those folds consists of 50% cat images, 50% dog images. That way, all random biases are taken out. So splitting it doesn't have to be 2. I just gave you a binary example, but look at this. We are trying to use this on 3 folds, right? We're splitting the data into 3 parts where we are what is our data? Basically, our data consists of 50 samples, and in those 50 samples, where are they coming from? Are they coming in from like a same columnar divided structured approach? No, it is coming from 2 unbalanced classes, right? This is something you guys have to understand as well. Even though the problem is very complex, once you start implementing it, ladies and gentlemen, it's a very simple way to implement it, to split your data out, store it in NumPy, and eventually get your machine learning model to use it effectively, train that many times, help you average out all these numbers and provide a usable output to you. Now, it sounds as simple as I say it, but is it actually this simple in Python is a question you might be asking. Well, let me minimize these, because the next code that we're going to take a look at is exactly that, answering that yes, it is actually that simple, right? Now, what we're going to be doing is we're going to pick up first of all, we're going to be generating some random data. Now, when I say generating random data, we are in the process of creating that particular data, right? So we're going to be creating the sample data set for us, which consists of 20 input features. You can see n_feature says 20. It means it's going to be 20 input features. And in those 20, right, now as I told you, there might be many factors that can cause diabetes. Someone just might say that this person wakes up at 5 o'clock, hence he might not have diabetes. Is it relevant or not relevant, or is it actually contributing to your final target of a person being diabetic or not? When we're assessing that, we can still go one step ahead and say, hey, out of all the 20 features that we're trying to divide, 15 of them are actually contributing to your target. 5 of them are redundant, right? So we have 1,000 samples of data considering with respect to 20 features, out of which 15 eventually help your target variable. 5 might not. It's redundant. Yes, you cannot remove it. If you put it out to 0, it will not hurt. But at the end of the day, we are trying to get really close to the real world, and there can be many points. In fact, this can be 10 and 10 each. 10 points might actually be redundant, while 10 other features might be very informative, right? So hitting play on this will definitely give us a data set which is, hey, there are 1,000 random samples that we are considering, which we have broken down into 20 features that we'll be using, right? This is the shape of X, this is the shape of Y. This is very important for you to understand, because the next couple of steps is all very simple, 1, 2, 3 lines of code, ladies and gentlemen, which will help you just achieve the entire process here, right? Look at this. We are importing how we can find out mean, basically average, right? We're going to be doing multiple folds. We're going to need an average of the accuracy. That's why we need mean. Next thing what we're going to do is we're going to find standard deviation. Now, once you find mean and you realize your data is distributed correctly, you can also say the standard deviation from the mean can be very low for your data. It means that your accuracy can be good, right? If your individual data point does not differ haphazardly from the mean, that is when you have realized your data is correctly split into multiple parts and it's working as it should in terms of training and in terms of assessing its accuracy with respect to testing as well, right? So that's why we require standard deviation. That's why we require the mean. After which, it's all very simple, ladies and gentlemen. We're going to be using a quick logistic regression algorithm, and we're going to be importing k-fold, and we're going to be finding out the cross-validation score. What is the cross-validation score? It's the final score after all that entire process, which tells you, hey, this is what the accuracy rate is, right? Now, let me zoom in a little. To go to that point, to do that, you have to understand you have to generate a data set. This is a part where all of you all are free to use your own data sets, to be honest. So if you're watching this particular course, you can do it alongside me. Import a data set of your choice. Now, just so that I can explain it to you, we're generating a sample data set which will basically get the job done. But if you have data sets that you have worked previously, you might have used the holdout method. Now is the right time to actually try to use k-folds and see if your accuracy scores have gone up, right? So once you have taken a look at all these sample data sets, and in our case, you have generated the data set itself, the next is to find out how many folds do we actually go on to do. And since we are using k-fold and not stratified, your data can or cannot be randomized. And you say that shuffle equal to true. Shuffle equal to true means yes, even though it's the random data that you're picking up in random order, still shuffle it one more time time and eventually break our data into 10 particular folds. N underscore splits equal to 10 is telling us that this is a 10-fold cross validation that we're going to be doing, right? So once I go on to run that, our k-fold model is set. So what do I have to do now? Now we know how the model has to train. So guys, as you can see, as soon as I actually ran this particular piece of code, right? So all we're trying to say is, hey, use logistic regression. Now you know how to go on to use the data. With this particular line of code, it has already done its training, right? So what's the next thing we do once your model trains? We try to figure out the accuracy, how accurate it is. Now, if we have just trained it once and we're testing it once, it's as simple as printing the accuracy score. With k-folds, we have cut the data out into 10 different folds and we've trained it that many times. So we have to make sure that we gather the accuracy score of all of those data points, combine it, club it into one score called as the cross-validation score and give us that, right? So as soon as I run this, that particular score will be ready. Once that is ready, all we try to do is find out and print the actual accuracy score. Now, as soon as I run this piece of code, it will tell me that, hey, your model is 86.8% accurate when you divided the data, shuffled it, randomized it, and used 10-fold cross-validation. What you see in the bracket, right? This is the mean. This is the mean of all the average score that we have, and this is the average standard deviation. Less the standard deviation means your data was actually better split. More the standard deviation, there's a very good chance your data was not split. So at this moment of time, if you're a person who wants to implement stratified k-fold, you can find that implementing stratified k-fold will tank your standard deviation, will make your data more aligned with respect to having all the features which are not redundant and which are useful for your Python outcome, right? So guys, with that, as I showed you, right, it is super simple to go on to work with k-fold, stratified k-fold, and just quickly generate a data set, implement it on your own, and work with k-folds to see what difference it does to your machine learning model. Right, guys? With that, we have come to the end of this course. We started out by taking an understanding of what cross-validation is, finding out if you have ever used it in real life. We try to relate so many things of how the real-world learning happens and how we teach our machines. We figured out that data is super important. We figured out the type of cross-validation that are. We understood exhaustive methods, non-exhaustive methods. We took a look at two fantastic non-exhaustive methods, the holdout method, which is very common. There's a good chance you might have used it, and the k-fold cross-validation method as well. And we figured out that there still can be some improvements we can do with respect to k-folds. That is when we took a look at stratified k-fold to remove random biases and make sure that every time we cut the data, it does justice for that particular training and testing iteration, right? So guys, with this, we also took a look at understanding all of this practically. I hope everything that I've covered in this particular course is clear to all of you all. Alright guys, thank you so much for watching this particular course. My name is Anirudh Rao and I'll see you in the next one.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell. This is done to make sure you do not miss out on any of the new updates or video releases from Great Learning. And of course, guys, if you enjoy this video, show us some love and do like this video. Knowledge increases by sharing, right? So make sure you share this video with your friends, colleagues, and everyone who can make use of it. And at the end of it, make sure to comment on the video if you have any queries or any suggestions, and I'll be more than happy to respond to all of your comments.